we're looking at more integration techniques, but I'm talking about integration. We're looking at partial fractions, decomposition. Okay. So that's the skill right there. Right. So we want to get into that. Right, so now let me bring in a problem to promote the idea. Okay, so let's look at a problem like this. Right, so we have, let's find, we want to evaluate, right, as minus 1 dx, for example. Okay, so let's look at a problem like that. So with this problem right here, I mean, if we're trying to get directly into the problem right here, then really there's no luck. And substitution methods or integration by parts, let me tell you, in my experience, it's not going to help. You can always find your own on your own time. You can always find a way to get it done right there with the earlier methods we've done, like substitution methods or the integration by parts. But again, let me tell you, it's not going to work so well, and that's why we keep needing. We have that need to keep looking for more methods right here, for more integration techniques right here. So to find the antiderivative here, right? And so now, here's how I'm seeing it. Algebraically, and you can see the following. First of all, the fraction here, this rational expression 2 over x squared minus 1 right here. Okay, I noticed that the denominator here can be factored into x minus 1 and x plus 1. Okay, it's just factor into x minus 1 and x plus 1. You guys all agree with me on that right there? Okay. And so because of that, so now I'm going to go a little further. And of course, right now, guys, I've done this for years, so the algebra has been quite fluent in me, but you can, whatever, after I'm done, you can quickly double check with me on this. But this will turn into this fraction. You can actually break it down into two separate fractions. It's a 1 over x plus 1. I mean 1 over x minus 1. Okay. There you go. So 1 over x minus 1 minus 1 over x plus 1. So algebraically, what I was saying earlier, algebraically, this 2 over the product of x minus 1 times x plus 1 will equals algebraically two separate little fractions right here. 1 over x minus 1 minus 1 over x plus 1. Okay? And why don't you guys take some time algebraically verify me? Take about a minute or so. Verify me. I hope you guys still remember the way. Make common denominator and multiply cross, right? To see if we end up with this. Okay, and with this 2 over that product right there, and 2 over that product is, of course, I'll be getting problem being the x squared, 2 over x squared minus 1. I want you to take about a minute right there to get that verified. Okay, check with this equality for me to see if I've done my math correctly. All right, so someone can start speaking up now, but do you guys agree? I hope you were spending some time verifying that.
Yeah, the graphs, they look equal on Desmos.
Yeah, it looks equals on Desmos. Okay, that's good. So these two are algebraically equals, right? Now, guys, be ready to be able to do this with the algebra, because Desmos does not always solve the problem for you guys graphically, okay? And we don't always have Desmos. But anyway, so this equals. The question you may have in your mind now is, how did I get this so quickly? And the idea is, of course, there was a method of doing this, okay? Otherwise, I'm not the superstar here. I'm not the Superman to know this so quickly. Right there. There's a method that runs behind the scene for me to break this down into two fractions. So we started out with one fraction. We broke it down into two fractions. That's the algebra of that, right? That's the algebra of that. And then there's a method that allowed me to do this. That runs behind the back of my mind right there. And I'll show you that shortly. But so what am I doing here? I mean, the idea originally, the problem originally was an integral problem. We broke that integrand, right, into two partial fractions, right? See, from one bigger fraction, one more complicated fraction, we turn it down to two partial fractions like that. That's why it's called, the title of our technique here is called the partial fraction decomposition. We're breaking it down like that. Okay? But now, why are we doing this? Why are we doing this partial fraction decomposition thing? Because now, think of your integrals here. This integral from the beginning, 2 over x squared minus 1 dx, right? Algebraically, this function as the integrand here will equal the integral of 1 minus x minus 1 as one term minus 1 over x plus 1 as another term. And then we can now integrate that. And so now with the advantage of having two separate terms, we can do the work term by terms. We can do the work term by terms. So on my, and I don't think I need to switch to the next board yet, but see, we can do that one separate term for x minus 1. And we subtract the antiderivative or the indefinite integral for 1 over x plus 1. We find the integral on two separate terms. Right? And so now the answer will be a lot more ready. Okay? The answer there for the first term will be just a natural log of x minus 1 in absolute value. With that one right here, you guys can easily and quickly do a little substitution for that, right? And you get natural log of x minus 1 in absolute value minus, and then now there's a natural log of x plus 1 in absolute value. That takes care of the second term after antiderivative. And then we add the plus c. We're done with the problem. Why don't you guys take a minute, differentiate this, take the derivative here so that you can make sure I land it back to the original function. Okay, original integrand right here. Okay, so take about another minute or half a minute to verify our final antiderivative here. So let's go back and dive a little further into the work that I have done here. Like I said, there's a whole mysterious process that ran from here to the two partial fractions. So we went from one combined fraction, right, into two partial fractions, which made it easier to integrate. So the point of integration, the integrating step is easy. It's not a big deal right there, but the part that takes you from a big fractions down to the partial fractions, that's where it takes techniques right there. And that's why the technique here we call the partial fractions decomposition. Partial fractions decomposition. We're breaking it down to partial fractions. Okay? So here's how I'm seeing it. So I'm going to have to erase and clear out the two boards here completely right here. So I'm going to start out with 2 over x squared minus 1. And you guys can see I wrote it down earlier that this was in factor form. So highlight this for me. Make a good note. You do need to be able to do your factoring. Okay? So be fluent with factoring. That's definitely a requirement. Okay, you got to be fluent with factoring. So if you're not sure, I mean, if you're still shaking with factoring, keep working. Grab an elementary algebra textbook right there, and keep reviewing your skill in factoring right there. They got to bring in all kinds of factoring methods right here. Okay, so you need to be fluent with factoring. So with this one here, it's easy enough. X squared minus 1 is the difference of two perfect squares, right? So we factor that into x minus 1 times x plus 1. Are we good with that still? And then the numerator on top is just a 2. So we got a fraction, and now notice, and the point of factoring is that each one of these is, any one of these, that's why I'm pointing the arrow here, is a linear, okay? Any one of these is a linear factor. Are we good? Okay, it's a linear factor, but then even on top of that, I want to optionally point out, for now, I want to make you guys aware of this, that any one of these is a linear factor, right? Because the power here is a power 1, and it's in the 1 times x minus 1, the ax plus b, the mx plus b thingy. Okay, that's why it's a linear factor. But then, other than that, right, it's also the two factors here. These are distinct, okay? Yeah, I have enough space to write. Distinct linear factors. Okay, so anyone in here is a distinct linear factor, meaning it's not repeated with another one, or it's not alike with any other one. And we'll get to some of the cases later on where we have repeated linear factors like that. All right, but now So now what? We factor out our denominator here into distinct linear factors. So let me erase out the notes right here. But the plan now is that the idea is that when your beginning fraction here, when the denominator of your beginning fraction can be factored into distinct linear factors, then now you're going to set up the following. It will definitely, it can definitely be broken down into the partial fraction where it contains only the x minus 1 with some coefficient a, and we need to find out what that a is. Okay? And then there's going to be another partial fraction being in the form of a coefficient b over x plus 1. So each one, the point is each one of your distinct linear factors will become a partial fraction in the form of the coefficient over just that distinct the linear factor, a coefficient over that other distinct linear factors. So here, since we had only two distinct linear factors, we will definitely end up with two distinct partial fractions right here. But each one of these is in the form of a coefficient over that factor, a coefficient over that factor. And in the world of algebra, it will always be plus. And once again, depending on how we found these values, a and b, it will turn out negative differently. It may become a minus sign later on. Okay, but that's the starting setup right there. So think about it. Think about before I advance further. Think about what ifs, right? What if it was like a 2 and then over an x minus 1 and then x plus 2 and then x minus 3, something like that. 3 distinct linear factors. Then your starting point is you're going to set 3 partial fractions, a over x minus 1, okay, corresponding to that. You're going to need a b over x plus 2, corresponding to this. And you're going to need a c over x minus 3 to corresponding with that, okay. And then at your starting point, it's all a sum of all these 3 partial fractions. That's how we're doing it. Okay, so I hope you guys are getting the idea right there of that thing. And so now, but I'm going to erase this extra work right here. That's just extra explanation. And you always can have access to these recorded video lectures right here. But anyway, so now with our current work, okay, so that's why it explains that our function here, our fraction here in the beginning got only 2 distinct factors. So we set it out as a starting point here. It's 2 separate partial fractions in that form. So now, think about if we're on our way to add these two, if we're adding these 2 fractions to combine that and make that into this final combined fraction, then here's how we're adding. Think about a over x minus 1. If we were adding it, then it has to be the following. We make common denominators, right? Common denominator will give me, which is simply, in the word of rational fraction, which is simply multiplying the 2 denominators together, right? And then a is going to have to multiply with, see, cross multiplication. So a will multiply with x plus 1. That's just the algebra. So everything here is completely algebra. B will multiply with x minus 1. Okay. So b multiply with x minus 1. And we plus 1. I mean, we added between the 2 terms. That's how we combine the 2 fractions into 1 fraction to get back to this beginning one. So this beginning one will equal that. But think about if we had the 2 partial fractions, turning it back into this combined fraction. That's how we're doing it theoretically. Okay. And so now we're going to work a little further. So that makes it equal. So I'm going to distribute the a into each term, and I'm going to distribute the b into each term. Make sure you guys raise your hand or jump in and speak to let me know if you need me to pause or roll back to any points, okay? Don't let me just go on. So now here we got ax plus a plus bx minus b all over that's x minus 1 times x plus 1. And then starting from this point right here, the denominator pretty much stays the same. But I'm mostly working on the numerator. All right. And so now at that point right here, again, I'm going to regroup you see these are common factors. There's the a times x and there's a b times x. I'm going to regroup them as an a plus b times x. That's one term right there. This is the x term, the combined x term. I'm combining like terms. And then now it's a minus b. I'm going to combine them as one combined term with those non-x terms. So this is a non-x term. That's a non-x term. So that's how I'm calling it, right? And so this is a plus, and then a minus b. Okay? Okay? So I'm just simply regrouping it, recombining it, combining the like terms like that. X minus 1 times x plus 1. That's how it works. Right? So now my numerator is supposedly, a plus b as one coefficient times x plus a minus b. And then the denominator here is just that same one right there, x minus 1 times x plus 1. Okay. So now you guys think of this. The whole idea of doing this, the whole reason of doing this, because we, in the end, what we want as a goal, we want this here. As a goal, we want, right? We want that a plus b times x plus a minus b all over that x minus 1 times x plus 1 like that, right? We want that to equal 2 over x minus 1 times x plus 1. That's what we want, because the whole reason of doing this, because we want that fraction here in theory has to equal 2 over all of that from the beginning. Okay. And once again, let me know if you have any questions or if you've lost any of the lost any of the steps I was doing. But now and of course you guys can always jump in and ask questions, but allow me to move on right here. But because we want these two fractions to equal, that's the way how it is. These need to equal each other. So the two fractions here already had equal denominators. So the only way now at this point, the only way for these two fractions to equal is that their numerators has to equal. So that leads to, so like I said, I hope I didn't miss anyone for this, but it's just because the denominators were already equal or being the same. So the only way now to guarantee the two fractions here being equal is that we're going to set this numerator on top here to equal 2. Okay? And so now I'm going to move over to the other board. So from having that equality right there, it must be true that a plus b times x as a polynomial plus the constant term a minus b. See, it's a polynomial. Think about the mx plus b, but now it's a plus b times x plus another constant term a minus b. That has to equal 2. Okay, that has to equal 2. And so now the art is here. It's a polynomial. The x term here with the constant term, the x term, the constant term, and in order for this polynomial to equal another polynomial, think of this 2 here as a polynomial being a 0x plus 2. That's what you think of that. 2x. Okay? 0x plus 2. 0x plus 2. I need more space, so I'm writing it like that. So now the only way for two polynomials to equal is that they're matching coefficients. So a plus b has to match with the 0 coefficient. Okay? Matching coefficients, because why am I matching those coefficients? Because they're all going with the x term. So for this left-hand side polynomial, the x term has coefficient a plus b, but the x term on my right-hand side polynomial is a 0 coefficient. So that means now matching means I'm going to equate a plus b. I need a plus b to equal 0. That's one thing. And at the same time, so in my style, I use the curly braces right here. But at the same time, the constant term a minus b got to match with 2 right here. That means, meaning a minus b has to equal 2. Okay, so once again, it's all due to the fact that we need the two polynomials equals each other. And again, further purpose, the reason we need the two polynomials to equal because we wanted these two fractions to be equal. And then the reason we want these two fractions to equal is because this fraction in the beginning is supposedly equal to these two partial fractions. And those two fractions, those two partial fractions, once we combine them, they're going to go into something like this. I hope that explains all of the reasonings. Okay? But now, back to this step that we're currently at. Think about this. What have we produced for ourselves? It's a system of linear equations here. Two variables, a and b, that we're finding out. A plus b equals 0 and a minus b equals 2. Now at this point, you can have your whatever favorite method to solve this. You can go with the substitution method for solving system of linear equation. I'm not talking about the integral. Substitution method to solve the system of linear equations, or you can go with elimination methods or whichever methods, or you can even plug it in and use a matrix. Okay, at some point I can also show you how you can use a matrix for this. But here I'm more comfortable, for this particular problem, I'm more comfortable with the elimination method. So adding the two equations here side by side, see, when you're adding it up, it equals 2 on the right hand side, okay, 0 plus 2, a plus a giving me a 2a, but b plus minus b is going to give me a 0. That's why it's easily canceled out and giving me a 2a equals 2. So 2a equals 2 will lead to a equals 1. We found a value. And now a equals 1. Back into this problem right here. If a equals 1, you can substitute a equals 1 into any one of these two equations. And you're going to look, so I'll choose number 1 right here. So 1 plus b equals 0 from that equation. So that means now you're looking at b equals negative 1 by subtracting 1 from both sides. Okay, subtracting 1 from both sides. That's what happened. Okay, and so in that way right here, we have found it. 1 plus b equals 0. Subtracting 1 from both sides, we end up with b equals negative 1. Okay. But so I said earlier a little bit like a whisper over here that we have found it. Found what? That means what? Now let me use that space right here. I'm now going to go ahead and erase all of the work here. See, so right from here in the beginning, to find a partial fraction, 2 over the two partial fractions for this fraction right here, 2 over x minus 1 times x plus 1, the two partial fractions, theoretically needed to be a over that plus b over that. But now we found out a is a 1, so it's 1 over x minus 1, okay? And b is a negative 1, and that's why the term was minus 1 over x plus 1. All right, so this is the reason why earlier in the problem, when I was back into doing this integral, right? 2 over x squared minus 1 as a dx, right? I turned that, yes, in factor form, it's 2 over x minus 1 times x plus 1, okay? And then I further went into turning that into a 1 over x minus 1 minus 1 over x plus 1. That's how I knew it. But that's how it's done. Okay? And then from this point on, we take the integral on each one of the separate terms here. All right. And so that's the method that we call the partial fraction decomposition method right here. We use that partial fraction. We turn a combined fraction into partial fractions so that we can break that problem into term by term thing. Okay, so that we can find our integral term by term. Okay, but then we turn that into like small fractions. All right. Any question for me?
Does it have to have 2 in the numerator at the start of this method?
Does it have to have 2 in the denominator? Good question.
Start of the method.
So it should. It should. It doesn't have to, but think about it. The point is, if it only had 1 in the denominator, think about the problem right in the beginning. If it was only 2 over x minus 1, for example, only 1 factor in the denominator. Is that what you're concerned about? Then this problem is too simple. This problem is too simple to the point that we don't even need any technique. You see what I'm saying there? And so now it's just with a problem like this, we just pull out a 2 right here, and it goes 1 over x minus 1 dx. I hope I understand your question correctly. So if it was only 1 distinct linear factor in the denominator, the problem was already easy. There's no need to go through this process. Okay, so this process is only good. It is only needed anytime that you got more than one, right? Multiple linear distinct the multiple distinct factors or multiple factors in the denominator. And it's only work for rational functions actually. Okay?
I was asking if it has to have the number 2 in the numerator at the very start.
Okay. It could be something else. It could be something else. And that's why so it could have been a 1 over x squared minus 1. Okay? And right now it's just completely out of my own creativity right there. Just to point out it doesn't have to be 2. Okay? So here's how I'm doing it again. So if your fraction is like that, then yes, right from here it's 1, right? We change that to 1. And we're always going to need the 2 templates like this. We always need a 2 starting point like that. Then with the 2 starting points here, right? Think about recombining them. Yes, then allow me to start going fast with the steps right here. We got a times x plus 1, right? Plus, and then a b times x minus 1, right? And all over that's denominator multiply together. Do you guys agree? Okay. And then all that here I'm going to recombine. So that's making it a plus b combined with x, right? As the x term, I got and plus a minus b, pretty much the same. All over the x minus 1 times x plus 1. Okay. And then we want, right? We want the a plus b plus the a minus b here over all that, etc., has to equal 1. This time we switch to a 1, right? It doesn't have to be always 2 right there. Okay, we can do that. And so similarly, on this board right here, the work will become we equating that with just 1. You see what I'm saying there? But this one in the end is very similar. It's 0x plus 1. Think about it. It's just a constant term polynomial. So now I'm setting up my linear systems. A plus b need to be equated with 0. Okay? A minus b now need to be equated with 1. Are you with me there always? And so now in that case, like the again, can just elimination methods again, we're ending up with 2a equals 1. That leads to a equals a half. It does change the value for a. So it doesn't have to be 2 at the beginning, but it can be whatever. But then the solving work here is a technique that will change your a and b value. And then from that you can easily find out that b will equals a negative 1/2. Okay, so that means ultimately speaking, if our problem from the beginning was a 1 over x squared minus 1, right, then the partial fractions will be found to be, it's a 1/2 over x minus 1. And then you can write it as a 1 over 2x minus 2. Okay, that's the same thing right there. And then minus a 1/2 over x plus 1. All right, that's the idea right there. And then you can rewrite that, like I said earlier, 1 over 2x minus 2, right? And then minus a 1 over 2x plus 2. You've got so many ways of writing it. But that's how you found the ideas, the method that we found for partial fraction decomposition is the starting point right here. Okay? And the first thing I show is that we recognize the denominator here as distinct linear factors. Distinct linear factors. Okay? Did I answer your question?
Yes, sir.
All right. Let's call that example 1. Okay? For this big topic right here. So we are not integrating because the bigger idea here is to use the partial fraction decomposition. So I'm just going to say find the partial fractions. How's that? Okay. Find the partial fractions. Okay. Of each of the following. All right. So let's look at part A right here. How about our fractions? So I'm not doing an integration problem. Just look right into a fraction right here. So let me find a good one. Here. So right now it's simply just an algebra problem. Really, it is an algebra problem. We need a lot of algebra. Right? So we got a problem like that, right? But now before you guys proceed, let me put in one note that is also quite important that I hope you guys also realize. Now, we only apply partial fractions decomposition methods into those cases where your numerator right here, see, numerator, okay, is a lower degree than denominator. You see, the denominator here is degree 2. The numerator here is degree 1 or less. The earlier problem was the same. The earlier problem where I promoted the idea like that, it was, see, 2 over the x squared minus 1, right? Numerator is here, degree 0. The denominator was degree 2. Okay? And that's why we needed to use a partial fraction decomposition. And then later on, and right now let's put aside the case where the numerator equals degree or higher degree with the denominator. We will get into that. Okay, but right now let's focus our work in here. We only the partial fractions only apply to those fractions where numerator is lower degree than the denominator. Thumbs up with that so far? All right. And so now let's get in. So for this work right here, we need to do the factoring. Okay, and you guys can double check this. But and there are so many different ways to argue about the factoring here. But the 2x squared plus x minus 1, okay, can be factored actually. We can factor that into an x plus 1 times a 2x minus 1. That's the first thing I noticed. Okay, and then the numerator doesn't need to get factored. The numerator doesn't have to be factored. So the first thing is to factor out the denominator into distinct linear factors. And right now that's a simpler case like that. And we will get into handling how it is a non-distinct. Okay, some of the repeat factors like that. We'll get to that. Okay. Are you guys following with me so far? And so now with the distinct linear factors, then here's how I'm starting. Okay. I need, so 5x minus 4 over the x plus 1, right, times 2x minus 1 right here. That's from the start will equal to, just like that template I pointed out right there. We need one distinct linear factor with a coefficient on top, a. Okay. We need one coefficient on top of the next distinct linear factor. So 2x minus 1, we'll get another we'll get another coefficient on top of that. All coefficients here, no x or no whatever. Okay, no x or whatsoever. Okay, and now we're gonna add these two partial fractions. That's what we do. So that's what I call the starting point, or a lot of times I call it's a starting template, a starting formula of how we get it to work. Okay, and so now with that, the work is going to become just like how I've done that, how I demonstrated it earlier. I'm going to think about we're going to need to recombine these, right? We're going to combine that with these two unknown coefficients. So it's going to be a times 2x minus 1 plus b times x plus 1. Okay? And we're dividing that over x plus 1 times 2x minus 1, that common denominator. All right. So that's one step, we're combining. And then remember, we're going to rearrange the terms so that we can recombine the like terms together. We can combine the like terms together. So first thing we need to distribute. We need to distribute these coefficients first. So in my next board right here, go ahead and take note as I'm erasing the other board. All right. So for the next one right here, I'm looking at, see, there's 2ax minus a, right, plus bx plus b here, all over that x plus 1, and really I can just simply skip out writing the denominator because it will always stay the same. And then now we're gonna combine like terms. So the x and the x terms are here. We're looking at 2a plus b. That multiplies with x. And then now it's all about an add. So minus a plus b, that's one term. So that's why we put that in parentheses, will be tremendously good. Okay, so that's a coefficient. That's the constant term over that x plus 1 times the 2x minus 1. Right? That's how it happens. All right. And then in that case right here, now we're going to need, so what we want here, right? What we want here is that we want this 2a plus b times x plus minus a plus b right here, all over the x plus 1 times the 2x minus 1 right there. We need all of that to equal the beginning fractions, 5x minus 4 over x plus 1 times 2x minus 1. We all want this to happen. That's what we wanted. Okay, and so in that way right there, here's how I'm doing it. See, that means we can just skip out the denominator. We just simply need, and I'm running short of space, so let me do this. That means that it leads to, logically, we must equate the two numerators. The only way for the two fractions with already the same denominator to equal, the only way for that, the two numerators gotta equal. Okay? And then now after we have isolated out the x terms, the constant term, the x terms, and the constant term, now we're going to start equating. 2a plus b has to match up, right? Has to match up with 5. Or another way of saying it, has to equal 5. Okay? Minus a plus b has to match up with minus 4. All right? You guys realize that we have just now produced another system of linear equations. 2 variables, 2 unknowns. Okay? And now you take your time solving this for me. All right. And you can easily divide, for this second equation right here, you can easily divide both sides by a negative 1 right there, and making it, you can turn that into a 2a plus b equals 5, right? And then the other one was a minus b equals 4 right there. And so now combining the two equations side by side right there, we're looking at 3a, right, equals 9. Are you following with me on that? Because the b here cancels out, right? And so that means a equals 3. See, we can still solve it manually. Okay? And then another one here, let's look at, and then now I'm going to take that equation when a equals 3, right? So we got 3 substituted for a in the second equation, minus b equals 4. So I'm going to subtract both sides by 3, okay? And subtract 3 from both sides, and then dividing both sides by negative 1. So it ends up easily with b equals negative 1 right there. Okay, so we found it. We found all of that work here. And so what we have done now, and I think I can fit it in all in here. Okay, so all of that we have done really come down to being, so the a over x plus 1, so a now has to be 3. So it's 3 over x plus 1. That's how we found it. Okay, and then minus 1 over 2x minus 1. That's the partial fraction for that. That's a partial fraction for that. All right, but this is all of that work right there. Right. And so, of course, with time being so limited, we don't have, it's impossible for us to get into another problem right here, but by the next time we meet, we should be able to bring in another one like that. But you guys already got the idea, the biggest idea has already been delivered like that. So for the rest of the lectures regarding this, it's all about we keep doing more problems so that it gets you into different experience here and there. That's all. But this is the method that we call the partial fractions decomposition. Okay? Let's look at part B now. So part B, you guys really already got a good hang of it. So I just want to bring up something. Okay, there's a square minus, and then there's a 3 here. Okay, so let's go ahead and use a partial fraction to find use a decomposition process here to find the partial fractions of this function right here. Want to find the partial fractions. That one. So why don't you guys take some time trying that independently like that, as you have seen the work and the action for that, right? So your starting point here is just simply factoring that out into, so that here is factor into, you can easily see that it's an x minus 1 and x minus 3, right? And the order of these doesn't really matter. So what you need at the starting point is a coefficient over the x minus 1, and you need another coefficient over the x minus 3. And right now we're looking at, see, after factoring, we notice there are the distinct factors, right? Distinct linear factors here, okay? So go ahead and get that done. What matters at the end is how we found that those values A and B. All right, so let me make that call now. How many people finished? About 3 people, right? So, just quick answer right here. What did you find for A right here? Who got A? Go ahead.
Negative 3 over 2.
Negative 3 halves, right? And what's B right there that you got?
3 over 2.
Positive 3 over 2. Yeah. And so here's the thing. You guys don't have to debate among each other about which one is. You have a way to check for that, right? Because if these are true here, basically the answer here means your two fractions here are going to have to be a minus 3 over 2 times x minus 1. You guys follow it? Right? Plus with a 3 over, because that's b, right? 3 over 2 times x minus 3. And then you have your way, you also have your reason. I mean, you also allowed to rearrange these terms, making it the 3, the positive term comes first, and then 3 over 2x minus 6, right? And then minus 3 over 2x minus 2, something like that, right? But then in order to check if you have found the correct A and B over here, go ahead and recombine them. See if you land into that precise expression from the beginning. Like make a common denominator and all that. See, multiply that through, right? Make common denominator to see if you guys agree right there. So I highly recommend, once again, try that, right? And then whoever you got your own answer, right? Try to recombine them to see if that all agrees back to this particular one. See what I'm saying? And that's how you check yourself. It's a technique that you learn the technique to get the broken down, right? To get the partial fraction, and you also have a way to check for yourself whether you made any errors or anything like that. And it's completely the algebra work. Okay. Right now we found minus 3 halves for A, and that's the thing about going to have, right? Your 3 over 2 times x minus 1 like that. Oops. 3, right? Minus 3 over 2 x minus 1. You can make the common denominator, making it's 2 here, right? X minus 3, x minus 1. Actually, you already had a factor of 2, so all you need is to multiply with the 3 times x minus 1, right? And then minus 3 times x minus 3 here. See what I mean? That's my flat work right here gives me 3x minus 3, right? Minus 3x plus 9 and over all that 2, and then x minus 3, x minus 1. That comes out canceling the 3x, right? 6 over that 2, and the x minus 3, and the x minus 2, x minus 1. And then the 2 got canceled, leaving out with the 3 over all of that, x minus 3, and x minus 1. So I believe your answer was correct. See what I mean? That's how you check yourself, right? And there should be only one pair of values once you found it. And with many people doing the same work right here, you should all agree with the same answer. So that's why I show that way for you guys to check yourself. So this work right here is not required to be shown on any of your written work, yes, but it's one thing that you can always check on scratch work, yes, to double check yourself. See what I'm saying? It's all the algebra, right? You guys surprisingly, you see you guys have gone this far if you count 2 right there, right? But the algebra is still going along with 2 right there. Okay. All right. And so yes, I agree with that work. So the whole example 1 is all about we breaking down into we decomposing a fraction into the partial fractions, but the whole thing here is any of the problems we've done, including the earlier example part A. In example 1, part A is all about when you factor it, right? It comes into the distinct linear factors, right? The distinct one. let me switch over to the other board to write down a couple of special remarks or a summarization right here. So far in our decomposition, right? If the work here goes some polynomial on top, and of course it's all just for the rational functions, right? And the denominator is built into like some. I got some a1x plus b1. These are all the distinct linear factors. So a2x plus b2, so on and so on, right? And then some an x plus bn. You guys recognize that what I'm trying to write? These are all just different linear factors in the denominator. Like the x minus 1 that you've seen just now in your example, that was the x minus 1, we're talking about a1 here is being 1, right? The slope, and then intercept being -1, things like that. So these are all different factors. So in that case, the way we do it as a general setup, again, as a general setup, we need a coefficient a1 for the first distinct linear factor. Okay? And we need another coefficient. That's why I'm giving indices. Otherwise, if we go with letters, then we're gonna trust me, you're gonna run out of letters. Right? Sometimes, I mean, we only have what 26, 24 letters or something like that, right? And eventually, you're gonna run out of letters. So we could use indices. So a1 over the first distinct linear factor, plus some coefficient a2 over the next linear distinct factor, so on and so on up to your last one, an right here over a n x plus bn. That's what we've done right here, right? When you have all distinct linear factors. First case, here, all distinct linear factors. Alright, so now let's swing back into this board here and let's get on with the other case. So what if we're not looking at distinct linear factors? So I'm going to promote a problem like this. And then now you're going to pick up things a lot faster here. So you got, how about the 3 again, right? Or maybe, okay, that's good enough. And then this is what I meant by the non-distinct linear factor here. How about x minus 1? And then there's an x plus 3 squared. That's what I mean by the non-distinct, right? Or repeated linear factors. So there's some repeated linear factors, whereas these are all distinct linear factors. Okay. So right here in this problem, we got repeated. Okay, repeated linear factors. Okay. So basically, now we get into a mix of some of those, some of the linear factors distinct, right, and some other ones are being repeated. But between these guys here, so the repeated means it repeats itself like that. That's the idea. But then among these, so we got 3 linear factors at the bottom, right? But only 2 of them are distinct, different from each other, right? But then these 2 guys are repeated. That's what we're trying to get into. See what I'm saying now? So here's how we're handling it. Right. Just like that. Now, for each of the distinct ones, let's just take care of all of the distinct ones. So distinctively, we got x minus 1, and we got x plus 3. You follow it? Okay. So you're gonna go a coefficient on top of each of the distinct ones, just like usual. We need a distinct coefficient on each of those, right? Just like that, distinctively. But then there's a repeat one. There's a one distinct factor being repeated. So now I'm going to have to produce like this. There's an x plus 3 but squared. Are you with me on that? X plus 3 or squared. And then on top of that, I need a cx plus b. So I need more like a linear thing, right? On top of that repeated one. See what I'm saying there? Right? Keep adding it in. And these are all coefficients. These are, right now at the starting point, these are all unknown coefficients. And actually, I'm misusing the letters here. It should be some D, not B. Right. Please correct that for me. Okay, I already lied. Sorry about this. Let's change this to only a coefficient, actually. Okay. Only a coefficient. We don't need a linear thing at all. Only coefficient. Okay. So now, once you set it up for here, then we are ready for getting the work to go. But of course, the work is going to get a little lengthy here, right? But it's the same philosophy right here. So we're going to think about, so now, tentatively, we want this fraction to be broken down into 3 separate partial fractions. That's our ultimate goal right there. But then we need to find out A, B, and C. So just like that, think about if we really were adding these, right, and trying to attempt making our way back into this beginning fraction, then here's how it works. We've got to first make a common denominator, right? So the common denominator will certainly be just x minus 1 times x plus 3 all squared. You guys following? Okay. That's the way how the common denominator is. But then the first numerator here, for A, we got to multiply with what? A here, it already had it. See, the rule of adding the fractions here, when A is on top of x minus 1, compare x minus 1 here with the whole LCD, right? Least common denominator here, then we need to multiply A with x plus 3 all squared. Okay, you know that's algebraically. Okay. Then plus, right? Now, the B factor over here need to multiply with something, but B was over x plus 3, so we need to multiply with x minus 1, and we need to multiply with an additional x plus 3. You are saying that. Okay. That's algebraically how we keep track of that. And then the C term, the C coefficient. The C coefficient was already on top of the whole x plus 3 all squared, right? So now when you're making common denominator and all that, you only need to multiply C here with x minus 1. That's only factor left. Sound good? Okay. And now we're going to start foiling out these things and distributing the B and the C and all that, right? And so, yes, the work will get a little lengthy. But what I'm having here is an A, right? And foiling out this, it's going to give me x squared plus 6x plus 9. You guys can double check me on that. Okay. And plus B here, after foiling out these two factors, I'm looking at x squared plus 2x, right? Minus 3. Right. And then I'll have plus C times x minus 1. And we'll get closer to being done like that. Okay. X minus 1, x plus 3, all squared. You good with that still? And then so yes, go ahead and distribute out and recombine the like terms. So A times x squared, A times 6x, A times 9, and all that. So let's rearrange it. From that word we had earlier. We're looking at now ax squared plus 6ax plus 9a plus, and watch out for sign changes, that's all. Bx squared plus 2 bx minus 3b, right, plus cx minus c. All of that over your x minus 1 minus x plus 3 squared. Agree with that still? And now we can rearrange, now we can recombine these. So the x squared terms, right, we combine them into one term here. So making it really a plus b with the x squared term. That's good. And then these are the x terms. There's 6a, there's a 2b, and there's a c right here, right? These are all the x terms here. So we're going to have the plus. In the word of algebra, it's all plus here. So we got 6a plus 2b, okay, plus c. That's with the x term. Are we good? And now with the non-x term, that's 9a minus 3b and minus c, right? So we have plus and 9a minus 3b minus c. And all of that here, see, 3 separate terms with 3 separate coefficients. A plus b is one coefficient. 6a plus 2b plus c is another coefficient. And then all that. right, over your x minus 1 times x plus 3 all squared. Okay. So now, at this point, we want, our goal here is that we want the whole a plus b, right, times x squared plus with that 6a, the exact same arguments that we made yesterday, the earlier lecture. Let's see, x plus, and then there's 9a minus 3b minus c. We want all of this here to equal 3. See where that 3 came from? Because we want this fraction, we want that fraction, ultimately we want that fraction to equal with, we want that fraction I circled to equal with this. But they already have the exact same denominator, so the only way to have those equal, the two numerators have to equal. And that's the reason why I added up with this setup right here. I want this like the polynomial to equal 3. Okay? And so keep in mind again that this 3 here is the same as, think of this 3 right here as a 0 x squared plus a 0x plus 3. You guys with me on that still? Okay. So now we have our right to equate and create the matrix for ourselves right here. So here we come with the matrix. So in order for the two polynomials to equal, their matching coefficients have to equal, right? So matching coefficients have to equal, I mean a plus b now need to equal 0. The a plus b is for the x squared term, has to equal 0 for the other x squared term. Okay. Right. The 6a plus 2b plus c being the x coefficients, right? On the left hand side of the equation now got to be equal to 0 as well. Okay. And further, we got what's the other one? The 9a plus, not plus, 9a minus 3b, right, minus c. That must equal 3 because we have set up for ourselves another system of linear equations, right? 3 unknowns, 3 equations. System of linear equations. You guys realize that? Okay. And so when things get large like this, I mean, at some point, if you're comfortable with using a calculator to run as a matrix, that's fine too. Otherwise, say with the traditional algebra method, it still works. It will always work. It's just taking more time. And so right from this equation right here, right, you can think about it, you can have a matrix. You see the columns for A right there, lining up, right? You got 1, 6, and 9, right? The column for the B variable, 1, 2, and negative 3, right? 1, 2, and negative 3. That's a matrix. You guys follow it? Okay? And there's a column for C right here. You don't even have a C here, but that means it's a 0 coefficient. So really it's a 0, right? 0, 1, and negative 1. Are we good? And this matrix here on the other side of the matrix, that's why the vertical line right here represents those equal signs. See what I'm saying? So on the other side of the equations, 0, 0, and 3. So you got an augmented matrix right here, 3 by 4, right? 3 rows by 4 columns here, augmented matrix. So you got a matrix like that. So we're gonna row reduce that matrix, but row reduce is a term that only the linear algebra people, which is a few courses away from now, use. But I'm telling you that a little ahead of time, a little bit. But here's how. So I'm gonna enter that into my software over here, and in the next lecture or so, I'm gonna show you how to use that with the calculator, which is more familiar to you. So you can just name that your matrix here, being some matrix A right there, right? And then now with software, we always gonna have to go by row. So the first row was a 1, 1, 0, 0. Okay? And we don't need that fancy line there actually. For software, a matrix is just a matrix, right? A rectangular structure right there. So we got the 1, 1, 1, 1, 0, 0, comma 0, comma 0. And I'm going to, for this software, only for this software, I'm using a semicolon right here for the next row. Right? So I'm separating it out right there. And so the next row here is going to be, so can someone go ahead and read it out for me right there? 6, 2, 1, 0. Right? And then the next row right here, go ahead and tell me the next row.
9, negative 3, negative 1, 3.
Negative 3, 1?
Negative 1.
Or negative 1, and shouldn't it be 3 right there, right?
3, yeah.
Thank you. Yeah. See, every technology has a weakness with it. Last one. Okay, so now once we're done with all rows, right, we close that bracket for this software, and then I want to hit enter. So the calculator here started. And so I'm going to run the RREF command right here on that matrix. And look at what it will show you. So this is the number right here. Okay. So these are the coefficients. That's the downside of this program that I don't really favor it so much with that. But so remember the first column here is for the A coefficient, right? Second column is for the B, and the last column is for a C right here. So let me write it on the board here. Okay. So back on the board, what I'll have with my marker. The way how that final matrix looks. The way how that final matrix looks. And you don't have to be, you don't have to really. Okay, so 0.1875, and then the next one here is 010, and then there's a negative, right? 0.1875, right? And then there's a 001 here, right? Being 0.7500. Right? And so what this means here is this means the A value. So that means A equals that positive number. You know what I'm saying? Okay? A equals that positive number. So 0.1875. And then the B column is for the middle row, right? So it says right here, middle column right here, but on row 2 it says you see B right there. Okay? B equals reading that out as a chart right here, minus 0.1875. You guys agree on that? Right. And then C value, C is right here, right? For the C column equals to 0.75. Right? So we found C equals 0.75. So 0.75 is easily in fraction of 3/4, right? Can you guys, now your calculator can handle this, 0.1875, right? Go ahead and convert that into a fraction right there for me. Your calculator has a feature of doing that. Your TI 8384, and then you go math, and then there's a math, and then there's a fraction feature. They don't have that program on this calculator, on this computer station, so it's giving me a hand tie right now, but your calculator can handle that.
What was it again?
You go hit on the math button, right? There's some sub menus, right?
Yeah.
And you see like a little arrow frag with them.
Yeah.
Okay, so actually you need to type in the number first, right? And you go hit on math button, and then convert that into a fraction like that. So put the 0.1875 into that into a fraction for me. 3 over 40. Thank you. Okay. This is about 3 over 40. Okay, so you fraction. You guys want to practice a little bit? Okay, you type the number first, whichever the number that you are attempting to put into fraction like that, right? You type it in the number on your TI 8384. And then you go to math, right, and choose that fraction, arrow fraction there, right? Choose that option right there, and it's going to convert the number into that. You guys agree on that still? Okay. And so now once you have that, so what have we found here? I'm going to put this away, and please don't even worry about copying notes on this software I'm using in front of you guys. It's not aimed at, it's not meant for our instruction here. It's just it's the tool I'm using right now. And so in the end, coming back to the problem right here, okay, we are ready for final answer. See, think about this. I wanted 3 over all that, right? Equals this setup right here. So now we found our answer. A was positive 3 over 40, right? And A was over that thing right here. So it's let me erase that part of it. And you guys been writing down the notes closely, right? So I definitely erase this. Right. So A now has been found to be 3 over 40, which is 3 over 40 times x minus 1. 3. The value for B was a negative, right? So now we'll put it as minus, and then there's still 3 over, that's a 40 times x plus 3. We good with that still? And then your last coefficient, C here, was a 3/4 actually. So now it's nearly a 3 over, right? And then there's 4 times x plus 3 all squared. But you found it, you found the partial fraction of your beginning fraction. Okay. See what I mean? All right, so let's look into some example here. Let's look at some examples. So let's call it example 2. And then I put these. I put this problem right at the beginning with your factors already. I mean, with your denominator already factored, because I don't want to waste your time doing the factoring. But be ready that sometimes you may be asked, right, to do the factoring yourself. Okay. See what I mean? And if that happened, if that's the case again, and of course, for my problem, really, I wouldn't put the problem that those problems are too challenging for your factoring. Okay, but the idea is that be ready that sometimes you have to find the factors yourself. In this problem, it's already had the factors. So this is how I'm seeing it. See, so you got a few distinct. You got only 2 distinct, right? But any one of these guys is all repeated. See what I'm saying? Huh? So the way how we're doing similar with the demonstration problem. So for the distinct linear factor, the first distinct one, right? Even though it's repeated, but in the whole picture, x plus 1 is the first distinct one. You're going to need x plus 1, and then x plus 1 squared. See what I'm saying? Huh? We keep increasing that power until we reach out to the highest power for that repeated one. Okay. I need a coefficient on top of that. I need a coefficient on top of this. It's all added. And then we're going to now move over to the next distinct one. So x minus 2. And then I need another fraction for x minus 2 squared. And I need another one for the x minus 2 cubed. That's the plan like that. Okay, so we go C, D, and E. So basically we are forming for ourselves a group, right? Or groups of those distinct factors, and then keep rising up gradually, trying to keep their powers in the denominator. That's the technique that you guys follow it. Okay. That's how we cover those distinct linear factors. So I'm going to have to need a lengthy amount of space here. All right. So now think about if we're adding these fractions, these partial fractions together. Yes, certainly it's going to have to be a very lengthy fraction. So a here is going to multiply with a is on top of the x plus 1. So when we multiply and making common denominator, we need another x plus 1, right? And then I need to multiply with x minus 2 all cubed. See what I'm saying that? Okay. And then the b coefficient. B was already on top of x plus 1 all squared. So when I'm making common denominator, I only need to multiply with x minus 2 all cubed. Okay. And for the c coefficient, c was standing above x minus 2. Right? So when I make common denominator, I need to multiply with x plus 1 with the square. And then I need to multiply with x minus 2 with the square. 2 more factors of the x minus 2. Sounds good? And then for d right here, I'm going to have to break it down as, I'm going to need to multiply with the x plus 1 squared and another x minus 2. For the last one right here, for e, C, E here, I'm going to need to multiply with E was already staying on top of the x minus 2 all cubed, so I'm going to multiply with the x plus 1 all squared. All right, and we're over all of that. And allow me to also write this as the LCD, but the least common denominator, just the least common denominator of all of those denominators. And so yes, now we're going to take some time following that out.